Right, so for reasons that are about to become much clearer at the end of this lecture, I'm also going to show you what a chi-square test looks like in Stata. So again, Stata, one of many statistical programs that you can use, a relatively common one, especially in the social sciences, and it lets you do everything we're doing and spits out the statistics you need in order to do your hypothesis test. So here I'm actually just going to show you the chi-square test for the example we've been going through using the class data. And so here our null hypothesis is that there is no relationship between gender and having been in a fight, and then our alternative hypothesis is that there is a relationship between gender and having been in a fight. The results that pop out of Stata look like this. So you have your command at the top where you're making a crosstab of fight and gender, and then you're telling it to run a chi-square test. Here, the fight and gender variables are coded like this. So 1 means a yes, 2 means a no. For gender, 1 means male and 1 means female. So you can see these are the same percentages, same counts, same everything that we've had throughout this lecture. Here we have the observed frequencies and relative frequencies. So we have in that first cell there 17 people who said they were male and had been in a fight, and then that was 68% of the men in the class. In the one next to it, again, we have 12 people who said they were female and had been in a fight, and that was about 43% of the women in the class. So this is all stuff we've seen already today. This is just how the program spits it out for you. We have our row marginals here and our column marginals here. So again, this should be looking relatively familiar. This here is our total, or N, so we had 53 people who answered the questions about gender and the questions about fight, and so are counted in here. The chi-square test in Stata also spits out the chi-square statistic for you, which in this case is 3.37. And then we have the p-value here, which is 0.066. So we just went through the interpretation of this, but again, based on this test and based on what you can see on this slide, we would fail to reject the null hypothesis at an alpha level of 0.05. So the difference between expected frequencies and observed frequencies that we saw wasn't big enough to give us evidence that would allow us to reject the null hypothesis about there being, no relationship between gender and having been in a fight. Which brings us to our final topic here, which is correlations. And as I said before, correlations are another way of looking at associations between variables, but they're used for variables that have ordered categories, and particularly ones that have a lot of ordered categories. So you can imagine if you had a variable like age, ranged from like 18 to 100, you wouldn't want to do a chi-square test where you'd have to have a different cell for every single year of age, right? So 18, 19, 20, 21, 22, and so on until 100. So a correlation lets you look at relationships between variables without having to plot out exactly how many responses are in each cell. And a correlation specifically is a measure of association between two variables. It also is referred to as Pearson's R or just R. And this R value that we're going to be looking at can be positive or negative and ranges from 0 to 1. And these two different aspects of it, so whether it's positive or negative and how big it is between 0 and 1, tell you information about the relationship between the two variables that you're looking at. It is a statistic that can be calculated when the attributes of both variables can be put in order, and again that means variables that are at ordinal, interval, and ratio levels. It is technically possible to compute correlations for variables that have only two categories, if those categories are not ordered, but that's not something that we're going to do here. So we're going to focus on just ordinal, interval, and ratio level variables. So variables where you have categories that go in order, you can rank them from least to most, biggest to smallest, so on. Anything where you're going in some kind of order. And in a nutshell, what a correlation tells you is what happens to one variable when the other variable increases. And more specifically, it tells you about the direction of the relationship between those variables and the strength of the relationship between those variables. So I'm not going to talk about what both of those things mean. The direction of correlation refers to what happens when one variable increases, and more specifically, whether the other variable increases or decreases when the other one increases. So if you have a positive correlation, as one variable increases, the other variable also increases. So an example of this would be as the amount of food you eat increases, the amount of full that you feel also increases. Probably my worst off-the-cuff example yet, but we're saying that as one variable increases, another variable also increases. So another example of variables that tend to be positively correlated are things like education and income. So as education increases, income also tends to increase. Again, if you're looking at lots and lots of people and sort of plotting out, people who have higher income tend to also have higher education. People who have lower income also tend to have lower education, and vice versa. Again, though, I want to highlight that when we're talking about associations between variables, we are not talking necessarily about, perfect prediction. And it's not that everybody with high education ends up with high income. It's not that everyone with high income has high education. But in general, if you look at, all the people out there, people who have higher income tend to have higher education and vice versa. So knowing someone's income would let you predict something about their education, or knowing someone's education would let you predict something about their income, even though you wouldn't be right every time. All right, so back to this. We're talking about having one variable increase while the other increases, and that would be a positive correlation, which if you were to graph it, it would look like a line that slopes up. And we're going to look at graphs about this in a second. If you have a negative correlation, you're talking about a correlation in which, as one variable increases, another variable decreases. So, to follow with the worst example, as the amount of food you eat increases, the amount of hungry you are decreases. Right, so you've got one variable that goes up and one variable that goes down. And that would be a negative correlation. I guess a more serious example of a negative correlation might be the amount of time you spend on your phone while in class is probably negatively correlated with, the grade that you ultimately get in a class. So more time on the phone or higher values on time on the phone is going to generally be correlated with, lower scores on assignments in a class. So as one variable increases, the other variable decreases. Again, it's not a perfect association necessarily. Some people will have high values on both, some people will have low values on both. But knowing about the amount of time somebody spends on their phone in a class will probably tell you some amount of information about how well they're going to do in that class. So you could predict one from the other and vice versa. So that would mean that they would be associated. And if you were to graph them, as again we're going to talk about in a second, you would end up with a line that slopes down. So again, this correlation is going to be based on this value called r, which goes from 0 to 1 and is either positive or negative. If it's positive, it means that as one variable increases, the other variable also increases. And if it's negative, it means that as one variable increases, the other variable decreases. So here are our graphs now. If you were to graph your variables with one on the x-axis and one on the y-axis, if you have a positive correlation, you have a line that slopes up. So here, the example being education and income. So as you have higher values of education, you also tend to have higher values of income, and vice versa. With the negative correlation example, be the idea that as you have higher values of time spent on a phone, you would have lower grades in the class. Yeah, that said, I've always thought that if you can learn while being on your phone in a class, more power to you. The other option, if you don't have a positive or a negative correlation, you have a zero correlation or no correlation. And no correlation doesn't look like a line that slopes up or a line that slopes down. It just looks like a big blob. And you can see that as one variable increases, there's no clear trend in what the other variable is doing. So you can't possibly predict the values of one variable from the values of another variable. So line that slopes up, line that slopes down, and if you were to try to draw a line of this blob's slope, it would just be flat because it's not going up or down. And so it doesn't tell you anything, you can't predict the values of one variable from the values of another variable if there's no correlation, because you've got high and low scores, for all values, and they're all just in a big blob. All right, the other thing that we can learn from correlations is the strength of the correlations. And correlations are said to be stronger when you can do a better job of predicting one variable from the other variable. And what it looks like when a correlation is stronger is it looks like it's more of a straight line. The strength of a correlation is described by how big that correlation number is. So R varies between 0 and 1. A correlation of 0 is no correlation, and a correlation of 1 is a perfect correlation where you can predict every single value of one variable from every single value of the other variable. But most of the time, and especially in the social sciences, what you get is something in between. And rules of thumb are that weak correlations are generally less than 0.4. And you can see we have a correlation there that's R is negative 0.03, which is that top middle one, where if you squint, you can see that there's sort of a downward slope there, but it really looks like a downward sloping blob. And so that's an example of a weak correlation, where there is some relationship between these variables. You can see that as one variable goes up, the other one generally tends to go down, but there's still a lot of random variation in there, and it's still relatively blobby. The stronger the correlation gets, so as you get into moderate correlations, like the one on the top right of 0.5, the one on the bottom left of negative 0.07, you can see that your relationship between the variables starts to look more like a line. Still kind of a blob, but closer to a line. Blob and line are the technical terms. No, they're not. But what they're describing is that, you can see as the values of one variable go up, the values of the other variable tend to go up as well. So by knowing that you have a high score in one variable, that tells you something about what you can expect from the other variable. But there's still a good amount of variation. There's still a good amount of sort of random scatter going on there, where if you tried to make a prediction, it wouldn't necessarily be a great prediction because there's not really that much of a one-to-one correlation between these two variables. As you get into strong correlations, on the other hand, you have relationships between variables where it really just looks like a line. And you know that, so like if we're talking about the one in the very bottom right there, where we've got our correlation of negative 0.99, it's very strong, it's very tight, just looks like a straight line sloping down. You know that if you have a variable that is high on one side, it's going to be low on the other side. You know that if you have a variable that's, low, the other one's going to be high. You don't have any cases where both of them are high or where both of them are low. It's always either high and low or low and high. And so when you have a strong correlation, you can do a really good job of predicting one variable from the other variable. So when thinking about direction and strength of correlations, you can combine the two ideas to get a picture that looks like this. Where here we have examples of correlations that are positive, but what they differ in is how strong they are. And here we have correlations that are negative, but they also differ in how strong they are. Where this is a very strong positive correlation, so it's pretty much just a straight line sloping up. And we know that whatever these variables are, they're very closely related to each other, and you can predict one from the other really well. Here we have a more moderate correlation where, you can predict it pretty well, but not great. Here we have a weaker correlation where it's sloping up, but it's not as strong a relationship. You still have a good amount of scatter going on there. In the middle, we have zero correlation where it doesn't have a positive or negative slope at all. It's just a big blob of dots, and you can't predict where one dot is from knowing the value of either of the variables that you're looking at. And then we also have weak, moderate, and strong correlations with our negative variables as well. We've got some examples here of correlations using the class data. So typically when looking at real correlations, they're a little bit more messy than what you see in those examples. But you can still hear we've got some relationships between these data. So both of these correlations are predicting or showing relationships between your confidence in getting an A in the class and different variables. So the first one is how long is your commute to school in minutes in a typical semester, and so yeah, not necessarily this semester, and how certain are you that you would get an A in this class? And here we have a correlation of 0.4. So this is a moderate correlation. It looks like a general blob that if you kind of look at where the dots are, there is an upward slope there. So people who have longer commutes also tend to have more certainty that they were going to get an A in the class. So it's a moderate positive correlation. These are the variables: how much weed do you smoke in a month, and then how certain are you that you'll get an A in the class. The relationship between these variables is a weak positive correlation, where you have a lot of responses clustered around just people not using any marijuana, so there's a lot of them just along that line on the very left. But there's enough of a relationship that we can say that in this class, people who smoke more weed tended to also have more confidence that they would do well in the class. So there's a weak positive correlation. And again, the thing to pay attention to there is that number where for both of these, R is positive, so 0.4 and 0.11, both positive. And then the size of the number, where 0.4 would be a stronger correlation than 0.11. So there's more of a relationship between commute in minutes and confidence in getting an A than there is between smoking weed and confidence in getting an A. But with both of these, you would be able to predict confidence in getting an A in the class from knowing how long somebody's commute is or knowing how many times they smoke weed in a month. And your predictions would be better for the commute time because it is a stronger correlation, whereas your predictions would be pretty bad for the weed one because it's a pretty weak correlation. So there's a little bit of a relationship there, but for the most part, whether you're confident about getting an A is going to be hard to predict from, amount of marijuana used per month. Correlations can also be used to do a hypothesis test to determine whether two variables are related in a population. And as with any hypothesis test, we're going to be looking at research or null and alternative hypotheses. Your null hypothesis in a hypothesis test for correlations is that the correlation between two variables is 0. So in other words, there's no relationship between those variables at all. You couldn't possibly predict the value of one from the value of another. And so the null hypothesis is that in the population, there is no relationship between two variables. Your alternative hypothesis is going to be that, well, there is a correlation between two variables in the population. And so we're going to be using sample data to see if we can rule out that null hypothesis that there is no relationship between two variables in the population. And we do that when we see a stronger correlation between two variables in a sample. In a hypothesis test for correlations, the only test statistic is just that correlation value. So whatever your correlation is, it tells you about what's going on in your sample, and it can also be used to find a p-value by plotting it on a sampling distribution. And from there, we decide whether to reject the null hypothesis. So I'm going to head over to the document camera one last time, just talk through a hypothesis test for correlations, what the alternative and null hypotheses look like, sampling distribution, that stuff. But for the most part, the format is the same as the chi-square test and other hypothesis tests we've met before. And the main difference is that we're using this R value that we're also interpreting to tell us about the relationship between variables in a sample. We're going to be using that to do the hypothesis test itself.